Hey, in this video I'm going to be reviewing the topic of stoichiometry. So remember that for any stoichiometry problem, there's always two things that you can say about a mole. First thing is just to relate it to what it means in terms of quantity. That's this relationship right here. The other is to say how much it would, if you had that many units of it, how much mass it would have. All right, so remember this number comes from the molar mass from this formula right here. So taking a look at this question, we can see that we would actually have to use both of these relationships. And that would be done by first using this relationship right here, converting grams to moles, and then using this relationship right here, converting moles to formula units. All right, notice the diagonally matching units in the crossbar. The next question combines a little bit from the solutions unit with stoichiometry. What's the molarity of a 0.75 liter solution containing 346 grams of potassium nitrate? First thing that we need to do is turn that into moles, which remember if you're going to use a variable, that's moles is N. Okay, and that would give 3.42 moles of KNO4. All right, and remember that we're going to use that in the relationship where the molarity equals the number of moles divided by the volume. All right, just making sure that the volume is in liters. So we can take 3.42 moles. We can divide that by the 0.750 liters. All right, notice here I rounded it to 3 sig figs because this has got 3 sig figs. In this problem, we're also going to round to 3 sig figs because both of these numbers here have 3 sig figs. And that's going to be 4.56 molar. Next one, calculate the number of grams required to make this many milliliters of a 6 molar solution. All right, so remember in all molarity problems, volume has to be in liters. So the first thing that we have to do is convert 50 milliliters to liters. All right, and we can do that with a one-step crossbar. You can also do it, there are other ways to do this, but if you just say that there are 1,000 milliliters in 1 liter, all right, dividing by 1,000, that's going to essentially move the decimal point 3 times to the left, 0.050. Actually, it would be 0.0500. All right, that gives this 3 significant figures, because if there's 3 significant figures in the original number, there should be 3 significant figures in your converted value. So that's going to be in liters. All right, so what we're going to do is we're going to say that molarity equals N over V. And what we don't know is the number of moles. All right, so we need to solve for N. That's going to be N equals molarity times volume. The molarity is 6.0 moles per liter. Notice I changed it to moles per liter rather than leaving it as capital M, because I'm going to be multiplying that by 0.0500 liters. All right, and that allows you to cancel out your liters, which would give us this number of moles. All right, notice here it's to 2 sig figs because this value right here only has 2 sig figs. So then we're going to take that many moles of sodium hydroxide and convert it to grams, and that's just through this one-step crossbar. All right, so remember when you finish the calculation to this, just make sure that you round it to 2 significant figures, because this has got the fewest number of significant figures in the problem. All right, remember this, whenever you say per 1 mole, this means like exactly 1. You could put, means 1.00 with an infinite number of zeros, so this would have an infinite number of sig figs. Finding the percent composition of the elements that are in copper 2 chloride. First thing that you have to do is figure out what the formula is. So copper 2 chloride, that means that the copper's got a +2 charge. Chloride, crisscross those, that means it would be CuCl2 after you do the crisscross rule. And what we're going to do is figure out for copper, that's going to be the mass of a copper atom over the mass of a copper atom plus 2 times the mass of chlorine atom. All right, so that's going to end up being, all right, so for copper, since there's only 1 copper in the formula, that's going to be your numerator here, And then you're going to do the mass of all of the elements combined here on the bottom. All right. When you're done, you multiply it by 100%. All right. To get the percent composition of copper, the difference, all you do is change what the numerator is. Notice that the denominator for both of these is the same on the bottom. Right. The bottom would essentially be the molar mass of copper chloride. All right. All right, the next two problems are just straightforward stoichiometry problems. All right, going from number of atoms to grams, that's going to be a two-step crossbar looking like this. You would want to round your number to actually two significant figures, because this right here is the thing that would control the number of sig figs in your answer. And this problem right here, it's going to be a one-step crossbar, all right, because it's just going from grams to moles, and we can do that with the relationship that relates grams to moles. And it would have three significant figures because this has got the fewest number of sig figs in the problem. All right, and the next problem, I just want to point out there's a little bit of a typo in the original problem where they had the +2s beside these, beside the metals here. You actually don't need those there. So in this problem, all right, how many grams of copper would be produced from the reaction of this many grams of chromium in this reaction? All right, chromium added to copper 2 sulfate produces copper, and chromium 2 sulfate. All right, so let's turn these word reactions into formula reactions. All right, so chromium is just going to be Cr, all right, plus copper 2 sulfate. All right, you do crisscross between copper 2, which means copper plus 2, all right, and sulfate, which is SO4 minus 2. Crisscross those, you're going to end up getting CuSO4. All right, we are going to, that's going to produce copper, which is Cu, plus chromium 2 sulfate, which is going to be CrSO4. All right, and again, you get that by crisscrossing chromium plus 2. All right, remember the plus 2 comes from the Roman numeral. All right, and the sulfate we can get from looking at the reference guide. Crisscross those, you get this formula right here. And let's balance this. All right, taking a look at things, it looks like everything is balanced. All right, we have it's 1 1 1 1. So again, I think it's always a good idea just to put ones in there for everything, just to remind you that those are going to be the mole ratios. All right, so how many grams of copper would be produced from this? All right, I actually would prefer this word right here to be could be produced, but let's just leave it with at that, and we're going to say all right, and this would be the setup for this problem right here. First, we need to convert grams of chromium into moles of chromium. All right, then we need to use the mole to mole ratio. All right, so for every 1 mole of this, and we get that number from the balanced reaction, we could generate 1 mole of this right here. That's where this comes from. And then we're going to convert moles of copper back into grams of copper. All right, again, you just use the molar mass of copper, and since there's only one atom in that formula, you can just read it straight off the periodic table. All right, first thing you're going to do in this next problem is that you need to balance everything here. All right, so it says what mass of phosphorus is needed to produce 3.25 moles of this would be tetraphosphorus decoxide. All right, so we're going to start off with what we know. We know 3.25 moles of P4O, sorry, that's O10. All right, we are going to use a mole to mole ratio where we know that 1 mole of P4O10 would require 4 moles of phosphorus, and then for every 1 mole of phosphorus, you can get the molar. Right, and this would complete the setup for that particular calculation, and your number should be rounded to 3 significant figures. All right, so remember these coefficients, those are counted values, so they're considered to have an unlimited number of sig figs. Okay, so one thing about this problem, the words here should actually be how many grams of lithium oxide could be formed. All right, and the reason for that is this, if this is how many are formed, that would be the actual yield, all right, instead of the theoretical yield. All right, so in saying could be formed, what we're doing is we're calculating the theoretical yield, which we could do. First, we're going to turn grams of lithium into moles. All right, we're then going to use a mole to mole ratio here, and then we're going to turn that back into grams of lithium 2 oxide. All right, and we get this many grams. All right, so what this is saying is that the actual yield is 12.5, and remember that the percent yield is the actual over the theoretical, and you're going to multiply that times 100%. So the actual yield is 12.5 grams. All right, the theoretical yield, and remember what theoretical yield is. It's the maximum amount that you could make from the reaction, all right, which is based on how much of the starting materials you have. All right, in this problem, it's actually made a little bit simpler because you're reacting lithium with oxygen, and if you're doing it in air, in any place that's if it's regular air, there's almost an unlimited amount of oxygen. All right, so we could assume that lithium is the limiting reagent in this problem, and we're going to multiply that by 100%, and that's going to be 89.9%. All right, so one thing about these stoichiometry problems, please make sure that you go back and you watch some videos where they have to determine what the theoretical, what the limiting reagent is. If you go back to the Canvas section where there's practice problems on determining theoretical yield, you'll see that process where you have to determine which one of those materials runs out first. All right, so that would be an important thing to review for this unit as well.